Okay, so let's do 15.6, which is surface integrals of vector fields. So an orientable surface S has two distinct sides, an outside and an inside. So when we orient a surface, we are selecting one of the two possible unit normal vectors. So as an example, say this bowl here is our surface. So this is the outside here, and this is the inside. And this is the boundary, the lip of the bowl is the boundary here. So in order to get from the outside to the inside, I have to cross the boundary. So you could have a unit vector sticking out this way, or you could have one sticking on the inside. So this is an example of a surface that's orientable. Okay, so not all surfaces are orientable. So a Mobius strip is an example. So let's take a look at a Mobius strip. So to create a Mobius strip, I take a strip of paper and I gave it a twist. Then I connect the edges here. That would be a Mobius strip, so let me just staple that. So I claim this does not have both an outside and an inside, it only has one side really. So let's say, suppose that was, we call that the outside there. So let's follow it around. Keep going around here. It's going to be a problem now because I'm both here. When I went around, I got to this location. So therefore, that can't be an outside. And they both have to be on the outside then, here and here. So you can see then it only has really one side, this surface. So this guy, again, is called a Mobius strip. And it'd be an example of a surface that's not orientable. Okay, so suppose an orientable surface S is subjected to a force field. So an example would be submerged in a fluid with velocity field F. The volume of the fluid crossing the surface S per unit time is called the flux of F across S. So let's look at an example. Okay, so I'm going to take a mesh and make it into a surface. So here's my surface, and say I take this mesh and I submerge it into some sort of a liquid flowing. So maybe like a white water. So it has chaotic velocities going through each of these little grids. So the toothpick sticking through represents the velocity of the fluid at that point. So you can see up here, that's pretty quickly going through that point. The one over here is a bit slower because it's not as long as that one, but it's in the same direction. And the one at the bottom here is actually going in. So these two on the top are going out, and this one's going in. So the flux would be the fluid crossing the surface per unit time. So you can see it's possible for the flux to be zero because these guys pointing in could cancel with the guys pointing out over here. So it is possible to have a zero flux, but it's pretty much the net flow through the surface. So again, just imagine this is submerged in some fluid. Okay, so now we're going to try and find a formula to find this flux. So let me draw another picture now. So we have this picture, so let's assume that let's say that R of UV is a parameterization of S. So that means you're in the UV plane, you're taking this D region, which is a rectangle, and it's going to map into my surface here under my R mapping. And let's look at the typical rectangle over here, calling it Rij. So I'm assuming the rectangle is delta U this way, delta V this way. So my Rij guy will map onto the little guy over here. And then you'll have your velocity field coming through here, so your fluid. So let me just show you with the mesh again. So with the mesh we have this. So the toothpick is representing the F right here. And so the grid system here, when you map it onto R, will make a grid system on the surface. Okay, now let's take a look at an exploited view of this guy here. Okay, let's do that. Well, before doing that, let me just mention that your D region here is A to B on U, C to D, and my delta U would be B minus A over N. My delta V would be D minus C over M. Okay, so let's keep going. So now the Rij was the rectangle, one of the small rectangles in the UV plane. When you apply R to it, it maps it into a little patch in the surface. That little patch isn't necessarily a rectangle or a parallelogram, but if you choose delta V and delta U to be small enough, it's approximately equal to a parallelogram. So it'll be this parallelogram with these vertices. So it'll be R, UI, Vj on this R, U, I, Vj plus delta V here, and these two are here and here. So pretty much Sij, this little patch will be approximated by this guy here. And I'm going to call this vector here W and this one V. So V then is going to be this one minus that, so this vector here. I'm going to apply the mean value theorem to it. So you can see the thing changing in this is the U components. So it'll be derivative with respect to U, what I'm calling UI tilde Vj, then it'll be times my delta U for some delta UI tilde between UI and UI plus delta U. Do the same with the W. So W is going to be RUI Vj plus delta V minus this one, which we have here. And you can apply the mean value theorem for this. Here the U's are constant, it's the V's that are changing. So it'll be derivative with respect to V, Vj tilde delta V. Okay, so now let's approximate the flux across the patch Sij. So let me draw another picture now. Okay, so let me draw another picture. Okay, so the flux across our little patch Sij is roughly equal to this I claim. So we're going to assume, so the bottom part is the patch. We're going to assume on the, well, it's approximation of the patch anyway. We're going to assume on this little patch the velocity is constant of the fluid. So the F is constant on this little patch. So pretty much then the flux will be the volume of this parallel pipette. So by theorem 5, go way back to theorem 5, the volume of a parallel pipette is going to be, the guy's taking it this way, dotted with the 2 down here, the 2 crossed. So it'll be the velocity guy dotted with RU cross RV. Well, I'm pulling out the delta V and delta U's outside the cross product here. So it follows then that the flux across S, or whole surface, will be adding up all the fluxes of all the little patches. And the flux of each of the little patches then we can approximate using this, but in the limit they'll equal. So then we'll have this, and we have a double sum. So this is going to be changing the two Riemann sums. So the first one will be, the first integral is going to be over D here actually. First one will be one of the integrals, and the second sum will be a second integral. So it's going to be a double integral. And so right here. So looking at the flux across S then, taking this limit, will change into two integrals, and it's going to be over D, where R of D is S. So this would be a way we can find the flux then. So it turns into a double integral of this guy here. Okay, so that's the idea of this section. So let's look at some examples. So we'll look at some examples actually in the next video. So let's leave it there for now. or just dummy, I just say repeat again. So this first limit will create this first integral will become a du. The second sum in this limit over here at the m will create the second one, and you'll be integrating over d. Okay, and again, r of d is equal to s. All right, let's leave it there.